Okay, so the first question is about titanium. Titanium, being a very strong metal, is used in making these bone replacements or making aircraft engines and so on. So you have to describe metallic bonding for the first question. Okay, so metallic bonding is like this, when you have some atoms closely packed together. So we could draw something like this. And these atoms will have lost their electrons into a delocalized sea of electrons. So we're going to put them as positive ions because they have lost some electrons. Okay, so, and then we have a sea of delocalized electrons. So we could draw something like this and say this is the electron sea. Okay, so we have a sea of delocalized electrons. And then these would be our titanium positive ions. Or you could write cations. These are closely packed together. Okay, so this is the metallic bonding. Then we have to see that titanium has a stronger metallic bond than calcium. So we can reflect this in the higher boiling point because as we boil the metals, we will break all these metallic bonds. So explain why titanium is stronger than calcium. So we need to look at the periodic table. And we'll find that titanium is over here in transition metal and calcium is a group 2 metal. So as a group 2 metal, it can lose 2 electrons. But as a transition metal, it can lose both the 2 electrons from here as well as the 2 electrons from they have added after the 20th electron, which is in the 3d orbitals. Okay, so titanium could lose 2 plus 2 electrons. If we had, say, iron, we could lose 2 plus 1, 2, 3, 4, 5, 6 electrons. Okay, so you can have 4 electrons to be lost. So calcium is in group 2. So it can only lose, it can only have have 2 electrons for delocalization. But titanium is a transition metal. So it can use 4 electrons in total. So we can say 2 is from the 4th shell and 2 from the 3rd shell, which is added after the 20th electron for delocalization. Okay, so if we have more electrons to be delocalized, then we have a stronger metallic bond. Okay, so stronger metallic bond comes by having more electrons available for delocalization, so you have kind of more glue is applied to stick together all these atoms. Part C asks you to observe a reaction. So in part C, titanium metal is placed into hydrochloric acid, and then this dissolves to form a gas and a solution with a purple color. And this solution tells you that the solution contains titanium free ions. So we need to get the formula of this gas. So when a metal reacts with an acid, the product will be hydrogen gas and the salt. Okay, so this gas will be hydrogen. And as for the formula, so I didn't get a mark. Okay, so you need to actually write H2. So be careful with these things in the exam. Make sure you give the answer that the question asks for. If it asks for the formula, please give formula. If it specifies the name, please write the name. If it says identify something, then you can write either the formula or the name. And the formula for the purple salt, so here it contains titanium free ions and we're using hydrochloric acid. So hydrochloric acid forms chlorides, which is Cl with 1 minus. And then we have titanium, which is 3 plus. So we need to swap the numbers to get the formula. Okay, so it will end up with titanium TiCl3. Okay, then you have to write a balanced equation for the reaction with state symbols. Okay, so let's try and write our equation here. So we have titanium metal, and we are reacting this with hydrochloric acid. We can also put state symbols. Titanium is a solid, hydrochloric acid is dissolved in water, AQ. Then we goes to the salt, TiCl3, which is a purple solution. So this is also in AQ, and the gas H2, which is G. And then we have to balance the equation. So we see that here the titanium is balanced, but then HCl only one here, but there are more than one on this side. So we see that we have 3 Cl, we have 2 H. So if we put a 2 or 3 here, we will have an imbalance. So we need to find the lowest common factor. Okay, so I think that will be 6, right? So we need to put 6 HCl here, so we could form 2 TiCl3 and 3 H2. But by doing this, we also added a Ti, so we need to put a 2 here in front of Ti. Okay, so this balance the equation. It's also possible to use 3/2 if you used 1 here and 3 here and 1 there. Okay, that's also a correct answer. So when titanium powder, a component of some fireworks, is ignited in air, it burns with bright white flashes, so forming a white powder, which contains titanium 4 ions. Now when metal burns in air, it forms the oxide. Okay, so here we'll have titanium oxide. This will be 4 plus, as given in the question, and the oxide is O2 minus. So we need to swap the numbers. But before we do that, we see that we can actually simplify this to 2 and 1. Okay, and then we can swap the numbers. So make sure you also simplify it. It's possible. Write in balance equation, so this should be easy. Titanium solid burns in air, oxygen gas forming TiO2, and that's balanced already. The type of bonding present in the purple salt and white powder, these are compounds of metal and non-metal, so we have ionic bonding. We have ions, the positive and negative ions. Draw dot cross diagram to represent this bonding for the white powder, TiO2. So we have to use outer shell electrons only. Now titanium, we have to show titanium with the bonding. So we need to think about titanium first. Titanium is around here. So we have, for the outer shell, we have the fourth shell, which is has 2 electrons, and then we go back to the third shell, which already has 8 electrons from previous up to argon, and then we add 2 extra ones. Okay, so in the third shell there should be 10 electrons. So titanium should be 2, 8, 10, 2 for the moment. But then we have formed the 4 plus ion, so we have to lose 4 electrons. So we'll lose these 2, and then we'll lose 2 from here. Okay, so we end up with titanium with, in titanium 4 plus, we'll have 2, 8, 8 configuration. So the outer shell with the electron left is this one. So we need to draw titanium with 8 electrons. This will be 4 plus ion. This one is our third shell. And then we have the oxide ion, which we know many times we have drawn this one. So oxygen has 6 electrons and it gained 2 electrons from the titanium. And we have 2 of these. A common mistake that I see in the exam is that some students will draw ionic compounds as covalent compounds. Somehow they cannot distinguish. So if you drew this one with the oxygen bonded to the titanium, somehow you will get the wrong answer, and you won't get any marks. So make sure you distinguish ionic bonding from covalent bonding. Okay, then both the purple and put this one up maybe. So both the purple and white substances are compounds of titanium. Better. Okay, so but only the purple salt dissolves in water, the white powder do not dissolve in water. So let's explain what factor determines whether they dissolve or not. So there are two factors. The first one is whether there is strong attraction between the ions in the lattice. Okay, so this is the attraction between the oppositely charged ions in the solid. Okay, this is called the lattice energy. So if you have strong attractions, then it is difficult to dissolve it because it's difficult to break the solid. The second one is the attraction between the ions and water. So this is called the solvation energy. So I want you to remember that in ionic bonding, the ionic bonding strength depends on the attraction forces between the ions very much. Okay, so it doesn't just affect the solubility, but also affects other properties like melting points or the hardness of the solid and so on. So suggest why the pale purple salt, which is titanium chloride, is soluble, but the white powder, the titanium oxide, is insoluble. So here we can see the difference is titanium is 3 plus, here is 4 plus, chloride is 1 minus, this is 2 minus. So the charges are higher over here. So we can say that the TiO2 has ions with higher charges. So there is stronger attraction between the ions. And let's stop here. Okay, so we can say that this has higher charges. We can also specify this is plus 4 and plus 2 versus plus 3 and plus 1. Okay, second question. Brass. Brass is a very common alloy. We find brass objects for many purposes. So the first question asks you to explain what is an alloy. So an alloy is a mixture of metals, mixture of more than one metal elements, maybe sometimes even small amounts of non-metals. Okay, so alloys, mixtures of more than one metallic elements. You could just write metals if you want. And we may include some non-metals also. So we need to illustrate this using brass. So for example, brass is an alloy of copper and zinc. So you should remember the composition of some of the common alloys in daily life, such as brass and bronze, okay, stainless steel, for example. cupronickel for the coins. Okay, copper is one of the metals present in brass. So in the pure form, copper is very soft and malleable, while brass is considerably tougher. Okay, so explain why the alloy makes the metal stronger. Okay, so basically, what we have is that in an alloy, so we can draw some pictures to illustrate this. In the pure metal, if this is copper, the structure is more like this, very regular packing. So when we apply a force, the layers could slide easily. Okay. But if we have an alloy, we have ions of different sizes. For example, a bigger ion of zinc may be fitting in there. So this will have some kind of interlocking effect. The different size atoms have an interlocking effect to prevent sliding of the layers. When brass is placed in the hydrochloric acid, it produces hydrogen gas, and part of the brass dissolves away. A brown-red powder is left behind. Explain this phenomenon. Okay, so we know that brass contains copper and zinc. Only one of them will react with hydrochloric acid, which is the zinc. Copper is unreactive because it's less reactive than, much less reactive, and less reactive than H plus ions, let's say, hydrogen. Okay, so it doesn't react with acid. So the zinc dissolves away, this is left behind. Okay, so we can say that zinc is more reactive and dissolves in hydrochloric acid. We could say that we could write an equation if we want. And the copper doesn't react. And is left behind. We have an antique brass object here with a green color, so we have to identify this compound. This compound is called the green patina. In chemical name, this is basic copper carbonate. The formula of it is basically a combination of copper carbonate and copper hydroxide. So you could work it out from, copper carbonate with CuCl3, CuCl3, copper hydroxide CuOH2. So we can put an OH2 here, and then we add a Cu over here. And we have to identify the three substances that reacted with the brass to form the green compound. The three substances that reacted would be water. You can tell from the elements here. We have CO3, we have OH, so there must be some oxygen, some water, and carbon dioxide. Okay. Give the name of the acid that will dissolve brass completely. So we need an acid that will also react with copper. Okay, and there's only one acid that we know that will react with copper. There's nitric acid, and it reacts by a different reaction that produces nitrogen dioxide. And now it asks for the name. Okay, so make sure you read the question. If it asks for the name, please give the name, not the formula. Okay, question 3, calcium and barium. Part A, we need to write a balanced equation to show the reaction which transforms barium metal into white powder in air. So this is about leaving this metal in air and they become a white powder. So we have to write the one for barium. So they reacted with oxygen, okay, and then of course the product is the oxide. Okay, so we have to work out the formula of the oxide, and we can work this out by knowing that these are group 2 elements, so there will be +2, oxygen is -2, so we get 1-to-1 ratio. BaO. Okay, they cancel out. And we can balance the equation. Okay, easiest way maybe to put a half here. You can also use 2 + 1 + 2. If you want to put state symbols, this will be solid, this is a gas, this is solid. In the exam, the question will tell you whether you need to add state symbols or not. if the question doesn't ask for state symbols, you won't be penalized if your state symbols were wrong if you added it. But you don't have to put it. If the question asks for state symbols, then you have to give the correct ones. And in those cases, you can be assured that the substances will be easy to work out whether they are solid or liquid or gas or AQ. Okay, it won't be anything that you will not have that you will have a difficulty knowing which state they should be. Okay, ionic radius of the ions are shown in the table, and we have to use this data to predict the type of ionic lattice the oxides of calcium and barium would adopt. So we can predict using the ionic radius ratio. So for calcium oxide, the ratio would be 100/140, 0.714. And for barium oxide, we will have a ratio of 135/140, and this will be 0.964. So we have to use the data booklet. This is the same one you will get in the exam. Have you downloaded these on Canvas? You can find the PDF or the data booklet so you know what data you will get and what you don't have to memorize. One of those is the table here, so you can find the ratios and the type of structures. So for 0.714, it falls in the range of octahedral or sodium chloride structure, and for the last one, it is cubic or cesium chloride structure. Okay, so this one is octahedral or NaCl structure, and this one is cubic, which is a cesium chloride structure. The metallic form of calcium adopts the face-centered cubic, while barium adopts the BCC structure. Which type of these structures have a higher packing efficiency? So we have to remember that the FCC structure is based on hexagonal packing, and the body-centered cubic is based on the square packing. So the hexagonal packing is close packed, square packing is not. Okay, so the higher packing efficiency comes from the close packing, which is the hexagonal, okay, which is the FCC structure. Draw a few of atoms of calcium and barium in a 2D layer to show the arrangements. So this is asking you to show the hexagonal packing and BCC packing. So calcium is FCC. So this is hexagonal packing, which means that they pack like this. Recovering from a cold. And barium has a BCC structure. So in a 2D layer, it is like this. So this one asks you for question about the melting point of the sulfate of these salts. Okay, so both are used in medical use. For example, calcium sulfate is plaster of Paris, okay, to heal broken bones, and barium sulfate is X-ray contrasting agent for the guts. So you have to know some of these common compounds and what their uses are. Based on the size of the ions, you have to predict which sulfate salts have a higher melting point. So we know that calcium is smaller compared to barium, okay? And draw something like this. Because how do we know this? Well, calcium is in the upper position in the periodic table, okay? So calcium is here, barium is in the bottom. So there's two extra shells in between calcium and barium. Okay? So the two shells will make sure that barium will be bigger. So if we have a bigger ion, the 2 plus charge is more dispersed. Okay, so you can say the 2 plus charge over here is concentrated in this space, but this one is more dispersed. Okay, so it will have a weaker attraction. So the positive charge will be more concentrated in the smaller Ca2 plus ion, and the positive charge is more dispersed in the larger Ba2 plus ion. So therefore, the attraction is weaker for the Ba2 plus. And SO4 2 minus, therefore it should have a lower melting point. And this will be our higher melting point. Do you understand this? It's a little bit more difficult. Draw a dot cross diagram and a line structure to explain the bonding in the sulfate ion. Okay, so sulfate ion SO4 2 minus, we have done this in class. So for the ions, remember always the sulfur or other elements are in the center. Oxygen surrounds it. Okay, so we can draw a simple structure like this first because we have 4 oxygens. And then we can put in the electrons. Now it's 2 minus, so we need to bear in mind that there will be 2 extra electrons coming in from the metal. So usually these extra electrons go to the oxygens. So we can even start off by putting in the 2 extra electrons that came from the metal. And then we can start with the electrons on the sulfur. Sulfur has 6 electrons. And sulfur is an element in period 3. So it had the third shell as the outer shell. The third shell can hold up to 18 electrons. So we can have more than 8 electrons. But for the oxygen, this is the second shell, which can only hold 8. So we need to distinguish, okay? We cannot put more than 8 in oxygen. So oxygen needs 8 electrons. So it has, all of these are group 6 elements, group 16 elements. So they have 6 electrons. So oxygen has 6 electrons. If you put its 6 electrons like this, you can form single bond there for these oxygens which has gained an extra electron. For the 2 oxygens which hasn't gained extra electron, it has to form double bond to get 8 electrons. So to put 2 electrons there and have 2 lone pairs. And then lastly, we can look at the sulfur. Sulfur has to satisfy all this bonding. So sulfur could put electrons here, here, 2 here, and 2 here. So that's 6 electrons for the sulfur. And overall, we have gained 2 electrons, so we have to remember to put a 2 minus charge. We want to draw a line structure, then we have 2 double bonds oxygens, and we have 2 single bonded oxygens. And these have gained electrons, so we can put negative charge there. The sulfates can be produced by adding calcium or barium metals in the sulfuric acid. Which of these metals react faster? Give the equation for barium metal. Okay, so reactivity increases as we go down the group. Remember, we saw how sodium was less reactive than potassium, and cesium is very reactive. So reactivity goes down in general, okay, for the metals. So barium is more reactive than calcium. So barium is more reactive, should react faster, and we can write an equation to show this reaction. So barium metal reacts with sulfuric acid, and the metal, when it reacts with an acid, we form a salt and hydrogen. So the salt here will be barium sulfate, and hydrogen gas is H2. The equation is already balanced, luckily, so we don't actually need to change anything. If you wanted to add the state symbols, this is a little bit tricky because barium sulfate is actually insoluble, so this should be a solid, where usually it's AQ. Okay, so this one is maybe a more difficult question. The next one is an easier question. Linking up these uses with the metals. So I just show you the answers here. It's important also sometimes to know what metals are used for. So this is a pipe organ. So this actually uses tin metal in the pipes. So this one links up to there. This is radioactive nuclear power station. So it uses uranium as the nuclear fuel. This is a catalytic converter for the cars. And the catalyst contains three metals: rhodium, palladium, and platinum. So we have a rhodium metal here. LEDs uses gallium or indium, things like that. Okay, so gallium is used in LEDs. This is a kitchen tap, and then there is a plating on the surface. This is chromium plating. Okay, so this is chromium there. The cooking foil here is aluminium foil, so you should know this one. This is not tin foil, by the way. Okay, try to trick you, but it's not tin. Although we call it tin foil historically. They used to be tin many years ago. Finally, the magnet used in the headphones contains neodymium. Okay. In the past, aluminium used to be very expensive because they didn't know how to produce it in bulk. Last question, potassium chlorate. So this one comes to thinking about ionic compounds again. So this chapter basically is surrounded with the chemistry of ionic compounds and metallic bonding. Okay, so looking at metals and the compounds. Potassium chlorate is a salt of potassium metal and chloric acid, which is HCl3. So we have to give the formula of the chloric acid. Given the formula of the chloric acid above, work out the charge of the chlorate ion. Okay, so chloric acid forms a chlorate ion. How can we work out the charge of the chlorate ion? Well, we know that H is 1 plus. Therefore, if we have a 1-to-1 ratio with the chlorate ion, it must be 1 minus. So it should be ClO3 1 minus. If we had H2 ClO3, then it would be 2-to-1, then therefore it will be 2 minus. But in this case, 1-to-1 ratio. So make sure sometimes you can work out the charge of some new ions by looking at the ratios in the compound, because it must be neutral in a compound without charge. Okay, so you can deduce something like that. So hence we have to deduce the formula of potassium chlorate. This is KClO3 because potassium is 1 plus. And we have to draw a dot cross diagram for the chlorate ion. So, and we have to also indicate the electron transfer for potassium chlorate. So we have to start with the potassium metal. Potassium metal has 1 electron in outer shell. And then the chlorate ion, we have to draw it. So we have to think about how to draw the chlorate ion. So always the Cl is in the middle and the oxygen surrounds it. This time 3 oxygens. So let's draw 3 atoms next to it first. And again, chlorine is group free, period free. So this is the third shell. More than 8 electrons is allowed. So we can start with this oxygen. We know that some of them have to form double bonds because it needs 2 electrons. Let's put 2 electrons of the chlorine here. And then here, let's also form a double bond. Now, this oxygen could also form a double bond, but if it formed a double bond, then there's no space for this electron to go. Remember, we have to leave a space so that this potassium electron could go to an oxygen. So we have to make it a single bond here. So we leave a space here. Before we finish, we have to think about the chlorine. Chlorine is group 17, so 7 electrons in the outer shell. We have used 1, 2, 3, 4, 5 in the black dots. So we need 2 more. Let's put these as a lone pair in the chlorine outer shell. So then in the electron transfer, this electron will go to the oxygen. and then would become a potassium ion with lone electrons, and a chloride ion with one electron up there. So we can draw it in this way maybe. This will be a single bond. Those are double bonds. Okay. So chloride ion has a high oxygen content. We can actually release this oxygen content to produce oxygen gas for emergency uses, like such as on the aircraft. Excuse my voice. Huh? Okay, so write a balance equation for decomposition of potassium chlorate. So you have to read the question carefully. Sometimes some students struggles with these kind of questions, trying to get you to write an equation for an unfamiliar reaction. But usually enough information will be given to you. In this case, the question tells you that it decomposes to form just oxygen gas and potassium chloride. So we have oxygen gas, we have potassium chloride, KCl. Then what we have to do what we're left to do is just to balance the equation. So in this case, you can see that KCl with one KCl here, but we have an imbalance of oxygen atoms. So it's a 2 to 3 situation. So we need to balance it by making this 2 and making this 3, right? In this case, the KCl doubled, so we have to make up for making this a KCl2, 2 KCl here, okay? And then another question of ionic radius prediction, just to get you practice this one. So KCl should be the smaller divided by the larger always, okay? Get a number smaller than 1. This gives you 0.735. And then the structure, you can look it up. 735 is just falling into the cesium chloride category. Okay, just. In fact, this KCl has a sodium chloride structure. Okay, so it's very close. Therefore, sometimes it's better to adopt sodium chloride structure. But according to the prediction, we have to write cesium chloride here. Just a case to show you that predictions aren't always correct. Okay, part E is about potassium superoxide, which is also similarly used for producing oxygen for breathing. But this one has to absorb carbon dioxide. Okay, so these ones, you know, the mask drop down automatically from the above you in the seat in the plane, and there is a catalyst inside which contains potassium chlorate, and it heats up, and then it produces oxygen gas. But in superoxide, you have to breathe, and then you recirculate your air. Okay, so write an equation for this. So potassium superoxide, firstly, the formula is KO2, and then has to absorb carbon dioxide. Okay, and then the product from this, if you actually know, this forms potassium carbonate. This is in the notes, and then potassium carbonate, and we put oxygen gas out. Then we have to balance the equation. So it takes some time to balance it, but then at the end, this is the answer. Give an application for the reaction. This is used in firefighting, for example, or sometimes in scuba diving. And this is not a question. This is just showing you can look at the gummy bear reaction.